Nuclear weapons, the most devastating armaments ever created by humans to date. These weapons, owned by only a handful of nations, once became the most terrifying specter during the Cold War between the United States and the Soviet Union. At that time, the United States was estimated to have produced 70,000 nuclear weapons, and as many as 31,000 were ready for use, ready to be launched. The Soviet Union at that time had even made 55,000 weapons, and 45,000 of them were ready for use. The combined total of American and Soviet nuclear warheads at that time, if all detonated, was estimated to be capable of annihilating life on the face of the Earth. Currently, most of these nuclear weapons have been disarmed. The United States and Russia each now possess 1,610 deployable nuclear warheads and a stock of around 6,000. Why do nuclear bombs possess such immense power? Where does that power come from? And how do nuclear weapons actually work? This video will discuss how nuclear weapons work. First, what is a nuclear weapon? A nuclear weapon or bomb uses nuclear reactions. The word nuclear comes from nucleus or nuclei, meaning cores, in this case, atomic nuclei. A nuclear reaction is the process of splitting or combining atomic nuclei. The splitting of an atomic nucleus is called a fission reaction, while combining is called a fusion reaction. Atomic nuclei consist of protons and neutrons. Protons are positively charged, while neutrons are uncharged or neutral. These atomic nuclei are surrounded by electrons, which are negatively charged. The number of protons within an atomic nucleus determines what element that atom is. For example, a hydrogen atom has 1 proton and 1 electron. A carbon atom has 6 protons. An iron atom consists of 26 protons. A uranium atom has 92 protons in its nucleus. In the atomic nucleus, there are also uncharged neutrons. You might think you already grasp the immense power of nuclear weapons, but just wait. The mechanics of a hydrogen bomb, which we'll explore next, go far beyond your wildest imagination. This isn't just about a big explosion. It's about a physical phenomenon that fundamentally transforms matter. So, make sure you don't miss the most astonishing part of this explanation. The same element can have a different number of neutrons. For example, the most common hydrogen atom's nucleus has no neutrons, but there are a small number of hydrogen atoms that have 1 neutron, and there are also those that have 2 neutrons. The same element, but with a different number of neutrons, is called an isotope. Because atomic mass is determined by the number of protons and neutrons, the definition of an isotope is often stated as atoms with the same atomic number, but different mass numbers. Hopefully this is clear so far. This concept is already in high school lessons. If you don't understand, then studying high school physics and chemistry is the initial capital needed to build a nuclear weapon, even though the knowledge gained in high school might only be 0.1% of the knowledge required to build a nuclear weapon. Let's continue. It was mentioned earlier that atomic nuclei are composed of protons and neutrons. Protons are positively charged and neutrons are neutral. How can an atomic nucleus be composed of several protons? Won't charges of the same polarity repel each other? Why can several protons unite within an atomic nucleus? This is because these nuclei are bound by a force called the strong nuclear force. The strong nuclear force is one of the 4 fundamental forces that allowed the universe to form. These 4 fundamental forces are the strong nuclear force, weak nuclear force, electromagnetism, and gravity. Among the 4, the strong nuclear force is the strongest. By splitting or combining atomic nuclei, a change occurs in this strong nuclear force. The force that previously bound the atomic nucleus is released as very large energy. In this nuclear reaction, there is a conversion of mass into energy. Mass is another form of energy. The amount of energy produced by this mass conversion is written in Einstein's very famous equation, E mc2. The atomic bomb dropped on Hiroshima, although its total weight was 4.5 tons, and the nuclear material inside weighed 25 kilos. The mass actually converted into energy was only 700 milligaules or 0.7 grams, smaller than the weight of a ring. However, the power from that mass to energy conversion was able to devastate a city. So how can we create a nuclear reaction? Basically, all elements can be split or combined into other elements, but it requires a very large amount of energy that humans do not possess. With a very large amount of energy, it might be possible to change one element into another, with more protons, for example, into gold. However, to date, only one has been able to do it: God. The element gold formed in the universe in a violent explosion resulting from the collision of two neutron stars. For nuclear weapons, the challenge is how humans can split atomic nuclei. For this, it is necessary to find the material that is easiest and most likely for a nuclear reaction to occur. This material is one whose atomic nucleus structure is unstable. This material is called fissile material, and the suitable material is uranium. Uranium is an element with 92 protons. Uranium has several isotopes, namely uranium-234 to uranium-238, meaning with a neutron count from 142 to 146. Among these isotopes, the one suitable for nuclear weapons is uranium-235. If uranium-235 is struck by one neutron, it will become uranium-236. This uranium-236 is very unstable and immediately splits in a fission reaction, producing barium with 56 protons and krypton with 36 protons. But this is not as simple as just bombarding uranium-235 with neutrons. For a nuclear explosion to occur, the uranium must be in a specific condition that allows it, namely supercritical mass. Supercritical mass is the condition where the mass and density of the fissile material allow a nuclear fission chain reaction to occur. For more details, let's look at how the atomic bomb works. The first type of atomic bomb is the gun-type nuclear weapon. This type of nuclear weapon is relatively simple and easier to make compared to other types. One example is the little boy atomic bomb dropped on Hiroshima. In a gun-type atomic bomb, in principle, uranium material is fired to collide with other uranium. Here's how it works. The nuclear material, which is uranium-235, is divided into two. Both are in a subcritical mass state, so a nuclear reaction cannot occur. For a nuclear reaction to be possible, these two parts must be united very quickly so that supercritical mass is achieved. The method is by firing. For this purpose, the two parts are placed inside a steel barrel, similar to a cannon or artillery barrel. One part remains at one end, the other part at the other end with conventional explosives behind it to trigger it. These explosives are detonated. The explosion from the explosives pushes the uranium cylinder through the barrel at very high speed. The collision of these two parts unites them so that their mass becomes supercritical mass, the minimum mass required for a nuclear chain reaction. That force is not speed. This increases the density of the uranium so that its state becomes supercritical mass. Enter text in this supercritical mass condition. It's time to fire neutrons into the uranium atomic nuclei. Neutrons come from a neutron initiator, which is a material like polonium and beryllium. This neutron initiator releases neutrons triggered by the pressure from the collision. In this state, when neutrons hit the atomic nucleus, a fission reaction or splitting of the atomic nucleus occurs. Neutrons unite with the uranium-235 atomic nucleus, turning it into uranium-236. The highly unstable uranium-236 immediately splits, and a fission reaction occurs. This fission reaction produces two new atoms, barium and krypton. The splitting of one atomic nucleus, in addition to releasing energy, also releases 3 neutrons. These neutrons then hit other atomic nuclei, and a similar fission reaction occurs. An exponential chain reaction takes place, multiplying rapidly. This reaction continues as long as it is in a supercritical mass state. This nuclear chain reaction produces a nuclear explosion. The little boy atomic bomb had a power equivalent to 15,000 tons of TNT. However, currently, this gun-type atomic bomb is no longer used. This is because this type is less efficient and its weight is relatively heavier. The next type is the implosion type. Implosion is difficult to find an equivalent word for in Indonesian. If searched in a dictionary, the translation is explosion, but more precisely, implosion is an explosion whose direction is inward, the opposite of an explosion, outward explosion. The parts of an implosion-type nuclear bomb are as follows. The main material is a uranium sphere encased in explosives. However, this sphere actually consists of two halves. The purpose is to keep this uranium in a subcritical mass condition. This sphere also has a cavity inside. The cavity within the uranium is filled with material that functions as a neutron detonator or neutron initiator, which provides neutrons to trigger or initiate the fission reaction of uranium. The material for the neutron initiator, for example, beryllium-9 and polonium-210 isotopes, are placed a few millimeters apart. When brought together by the explosion's pressure, they release a large number of neutrons. Surrounding the uranium sphere is a neutron reflector. This is made of a material capable of reflecting neutrons like a mirror. The material used is usually beryllium. The function of the neutron reflector is to prevent neutrons from escaping during the detonation process. Outside the neutron reflector, it is wrapped with conventional explosives. When detonated, these explosives will press the uranium sphere from all sides, compressing it with great pressure, thereby increasing the density of the uranium until it reaches a supercritical mass condition. The uranium sphere and the neutron reflector are separated by a vacuum or empty space. Its function is to provide a tamping effect when the explosives are detonated, so that the explosion's pressure is focused inward, not bouncing outward. When the supercritical mass condition is reached, at that very moment, the neutron initiator in the center of the uranium sphere emits a large number of neutrons. These neutrons trigger a fission reaction, and a chain fission reaction occurs, producing a nuclear explosion. The implosion-type nuclear bomb that was used was the bomb named Fat Man, dropped on Nagasaki. This nuclear bomb used plutonium material. Plutonium is made from uranium-238. Uranium-238 is bombarded with neutron radiation. The nucleus of uranium-238 absorbs a neutron and becomes uranium-239. This uranium-239 then undergoes decay and transforms into the element neptunium, then into plutonium-239. Current nuclear weapons derive their power from fusion reactions. The fusion reaction, or the combining of atomic nuclei that occurs in modern nuclear weapons, is the combination of deuterium and tritium to produce helium atoms. Deuterium and tritium are hydrogen isotopes with 1 and 2 excess neutrons, respectively. Therefore, this nuclear bomb is often called a hydrogen bomb. Fusion reactions produce much more energy than fission reactions. The fusion reaction of hydrogen combining to form helium is the same as what happens in the sun's core. Inside the sun, this nuclear reaction can occur because hydrogen atoms are compressed by the immense gravitational force due to the sun being 330,000 times the mass of the Earth. Fusion reactions of hydrogen isotopes are also only possible at very high temperatures. The temperature required for this fusion reaction is around 100 million degrees Celsius. Therefore, hydrogen bombs are also called thermonuclear bombs. To simulate large pressure and high temperatures, an explosive energy initiator is needed. Conventional explosives are insufficient, so a larger energy source is needed, namely a nuclear explosion with a fission reaction. So, a hydrogen bomb works in 2 stages, a fission reaction and a fusion reaction. The pressure, radiation, and heat from the fission reaction in the first stage are used to initiate the fusion reaction in the second stage. Currently, scientists are still looking for ways to create a pure fusion nuclear bomb. But so far, they have not succeeded. Here is how a hydrogen bomb or thermonuclear bomb works. A thermonuclear warhead consists of two parts. The first part is a fission nuclear bomb with uranium fuel. This part is an implosion type, whose parts and working principle have been explained above. We call this part the fission sphere. Then the second part is for the fusion reaction. This fusion reaction will combine hydrogen isotopes, namely deuterium and tritium, which will produce helium. Hydrogen has three isotopes. The first is protium, where its atom consists of one proton and one electron. This is common hydrogen found in nature. The second is deuterium, whose atom consists of one proton, one electron, and one neutron. The third is tritium. In its nucleus, in addition to one proton, there are two neutrons. If deuterium and tritium are combined, they will produce a helium atom consisting of two protons, two electrons, and two neutrons. The problem in making a hydrogen bomb is the tritium element. Because tritium is unstable, it quickly releases its neutron and turns into deuterium. For this reason, in a hydrogen bomb, tritium is produced inside the bomb during detonation. Here's how it works. The process begins with the detonation of explosives around the uranium, which then triggers a fission reaction as explained before. This nuclear explosion, in addition to producing shock waves and heat, also emits very large gamma and X-ray radiation, in addition to emitting neutrons, of course. This warhead is wrapped with a beryllium layer. This beryllium material acts like a neutron mirror that can reflect neutrons as well as radiation produced by the fission reaction. The second part is cylindrical, with a uranium-238 casing, then filled with fuel in the form of lithium deuteride and a plutonium core. We call this second part the fusion cylinder. The space between these parts is filled with styrofoam. The heat and radiation from the fission reaction turn the styrofoam into plasma. What is plasma? Plasma is one of the four states of matter. If you were taught in school that there are three states of matter, solid, liquid, and gas, then above gas is plasma. The plasma condition occurs when the temperature is very high. In the plasma condition, the electron arrangement in the atom separates from the nucleus and becomes free ions. Gamma rays, X-rays, and neutrons produced by the fission reaction hit the uranium casing and the plutonium core in the fusion cylinder. A fission reaction occurs in both the uranium casing and the plutonium core. The pressure from both explosions simultaneously compresses the lithium deuteride from outside and inside. The lithium deuteride absorbs neutrons and produces helium and tritium. The generated tritium then combines with deuterium, and a fusion reaction occurs. This fusion reaction, which produces helium atoms, releases a very large amount of energy. A nuclear explosion results from the fusion. The entire process described above happens in a very short time, namely 600 billionths of a second, 600 picoseconds. That means 1 second divided by 1 billion, then multiplied by 600. For illustration, one blink of an eye takes 300 milliseconds, or 1/3 of a second. So the time it takes to blink an eye is 500,000 times longer than the complex thermonuclear bomb detonation sequence. In addition to the nuclear weapons mentioned above that already exist, there are other types that are still being developed or are theoretically possible to create. Among them is the neutron bomb. This bomb is a thermonuclear bomb with minimized explosive power, but produces a very large amount of neutron radiation. Neutron radiation does not damage physical buildings, but damages organic cells. Theoretically, when detonated, the city's infrastructure will remain intact, but humans will die because high technology is needed to make it. Only a handful of countries currently possess nuclear weapons. There are 6 countries that have nuclear weapons and are ready to be launched. They are the United States with 1,610 warheads, Russia also with 1,610 warheads, the United Kingdom with 120, and France with 280. China and India's exact number of deployable warheads is unknown, but they have produced 290 and 140 nuclear warheads, respectively. Pakistan and North Korea have successfully built and tested nuclear weapons, but their ability to launch them to other countries is still doubted. Iran is suspected of continuously developing nuclear weapons. It is estimated that they will soon succeed. Israel is strongly suspected of possessing nuclear weapons and the means to launch them. They are also suspected of being responsible for a mysterious nuclear test in the southern Indian Ocean. The flash of light from that explosion was recorded by the Palapa D satellite in 1979, but to this day, regarding nuclear weapon ownership, Israel has never acknowledged it, but has also never denied it. Incredible, right? From the physics of atomic nuclei to thermonuclear bombs capable of wiping out cities, we've seen how this immense power is unleashed. But did you know there's another, even more controversial and terrifying type of nuclear bomb, specifically designed to kill living beings without damaging buildings? Don't miss our next video to uncover the mysteries of the neutron bomb and why some nations still keep their nuclear weapon ownership a secret. Hit that subscribe button and turn on notifications so you don't miss out.